So on that note, let's get it started. Up first is Robin Wordsworth.
Great.
Just so you know the time.
Oh yeah, awesome. Thank you, Sean. Can everyone hear me okay with this mic? Sounds like it. Yeah, so hi everyone. Thanks to the organizers, first of all, for inviting me to talk here. And a third emphasis at that point, please stop me at any time if there's anything that doesn't make sense or you have a follow-up question on anything I'm saying. So I've been asked to talk about comparative atmospheric evolution, and this is a super broad topic. So I will here mainly be emphasizing a few things that I'm particularly interested in. And I'll mostly focus on the solar system because that's where the majority of our data is at present, but I will be talking about how it extrapolates to exoplanets as well. Final thing I was asked to do is not say too much about the Earth because Kevin Stanley's covered it. So this is what we're going to do with the Earth. Actually, that's not completely accurate because I will have one slide, so let's sort of leave it like that. So now I've sorted the visual representation of my talk. Let's go on to the text-based version. So my talk outline is I will begin starting with gas giant atmospheres, which in some ways are simpler to understand than atmospheres of smaller bodies. We'll then make the transition to the so-called metallic atmospheres. And so I gather this is an astronomy strong audience. So anyone who doesn't have the astronomy background, by metallic we mean things that are heavier than hydrogen or helium. I'll say a little bit about that in a general way, and then we'll go on to talk about atmospheric escape processes, some of the fundamental physics of what we think the most important escape processes are. And then from there will be a sort of run-through of the solar system, starting with Venus water loss and the runaway greenhouse. I want to say a few words after that of how water loss proceeds, or perhaps didn't proceed, on planets like Earth and on Mars, which have very different physical conditions. I'll say a little bit about icy satellite exomoon water loss, just because I think it's an interesting topic. And then the final thing will be a discussion of taking the theory and the knowledge we have from the solar system and applying it to exoplanets. How much water loss do we expect? And in particular, how much abiotic oxygen do we think might be produced in planets' atmospheres? Because this is, of course, very important for thinking about oxygen as a biosignature when we're searching for life. So, okay, let's go to the very start and say, thinking about planetary atmospheric evolution, how do we define a planet in the first place? I think really the universal way to do this is by mass. So we can start with the sun, a G-class star, which is hydrogen burning, primarily on the proton-proton chain. Then we go down. I'm going to try and use this laser pointer, but it might mess up my slides. Yeah, I haven't figured that out. Bottom part. Ah, there we go, yeah. So you have a star like the sun, which is not a typical star for the galaxy, but you go to lower mass and you get red dwarf stars, M stars, that are the most common type. Still burning hydrogen, but you keep decreasing mass and eventually you get to the point where you're no longer high temperature enough in the interior to fuse hydrogen. So there's a small period where things like deuterium burning can occur in the brown dwarf regime. But ultimately, you get even lower mass than that, and eventually you transition to a body like Jupiter, which is held together by the relic heat of its formation rather than any interior nuclear physics process. Okay. Doesn't want to respond. Yeah, it's doing something strange. Okay, thanks. So yeah, the second question then is if we define a planet by mass, what are planets made of? We can start by thinking about just galactic elemental abundances. So we have a whole range of elements here as a function of their atomic number, logarithm of abundance on the y-axis. And so firstly, you have hydrogen and helium, which are primarily made in Big Bang nuclear synthesis. There's then a bunch of elements which are made by thermonuclear fusion in main sequence stars, with, interestingly, 3 elements, lithium, beryllium, and boron, which are very low abundance. And then others which have various peaks in this characteristic zigzag pattern, the details of which I'm not going to go into, but it emerges from stellar nuclear synthesis. And then finally, once you get beyond iron, there's the whole range of other elements which are forming through neutron capture. And important as these are, as you saw in Kevin's talk for understanding the data on planets like Earth, they're not important to the bulk composition of any planetary atmospheres that we're going to talk about here. So from now on, we're going to be focusing on everything in this regime. So given these elemental abundances, what happens to gas giant atmospheres? Well, as Sean's talk described in a lot of excellent detail, you have a process by which you form planetesimals and eventually icy or rocky cores for gas giants. And then once you reach a critical point, this can start to capture the surrounding protoplanetary nebula, and you get buildup of a gas giant planet with some rocky, icy core and a hydrogen envelope on top of it. It doesn't just stop once that happens, though, because the major core elements are all soluble in hydrogen at the temperatures we expect in the interior of Jupiter and Saturn. So what's most likely to happen is that it dissolves into the interior. And this is something expected from theory, but also the recent evidence from the Juno mission suggests this is indeed what's been going on inside the core of Jupiter. And there are interesting details like layered convection, which probably alter this picture to some extent, but aren't critical to what we're talking about here. What is, I think, critical from an astrobiology perspective is that because of this process, we don't expect solid boundaries anywhere inside a gas giant planet. And so for probability of life, this has major, major implications. Gas giant atmospheres are not in chemical equilibrium because we have photons from the sun that impinge on them and cause them to drift away from that, particularly in the upper atmosphere. If they are in perfect equilibrium, because hydrogen is so abundant, you expect the key species to be, for heavier elements, to be methane, H2O, ammonia, and so on. But there's condensation, first of all, which causes them, depending on the equilibrium temperature of the planet, to freeze out at various pressure levels. And then there's the photochemistry, which is coming from the solar photons. And so a very generic kind of example for a Jupiter-like planet is that you would have methane coming in up here, getting photolyzed by high-energy solar photons, and then forming hydrogen and longer-chain hydrocarbons. It's thought that you can even get prebiotic or sort of precursor types of molecule like HCN coming out of this process. But this is probably not very significant from an astrobiology perspective, because once they form, they mix slowly down into the interior, and then eventually you get to a temperature where everything can just thermalize again and relax back to its chemical equilibrium. So we think of gas giant planets as bad places to look for life, not primarily because they're all in chemical equilibrium, because they're not, but because there's no solid boundaries to concentrate interesting molecules to a degree that you could start to do more complex chemistry with it. And so this is the Sagan Astrobiology Conference, so I can't talk about gas giants without mentioning at least something about floaters and sinkers. For those of you who don't know about it, this is an idea that Sagan had at some point back in the 70s for potential for gas giant life forms. And I think it's just a wonderfully imaginative idea, but of course it's entirely unsupported by any observational evidence. So gas giants are interesting objects in their own right, but perhaps a little less so for astrobiology. So let's now transition to talking about lower mass planets, the rocky planet transition. One of the things I think is amazing about this decade, the 2010s for exoplanet research, is that based on exoplanet data, we can now actually visualize this transition directly. And so it's now apparent that if you get to a radius above about 1.6 Earth radii, usually a significant hydrogen envelope is going to be present around that planet. So this plot here is showing you mass in Earth masses, radius in Earth radii, for a bunch of observed exoplanets, and you can see at low masses, you're falling on this line that we see for Earth and Venus, and at a certain point, you get a jump up towards much larger objects. So the transition occurs in mass terms in the 5 to 10 Earth masses range. I think it probably should be apparent already from the talks we've already had that these atmospheres of planets in this regime, the so-called metallic atmospheres, where it's not hydrogen or helium dominated, it's generally a complex and nonlinear process and requires much more modeling for us to understand it in detail. So let's talk about a few of the aspects of this, which I think are particularly significant now. Before we do that, I just want to say some words about some basic chemistry concepts. And well, if you've trained as an undergrad in physics, as I have, then maybe sometimes there's a tendency to say about chemistry, well, I know what a Schrodinger equation is, and you can apply that to atoms and nuclei, and then everything kind of emerges from that. So you can sort of take this overly confident, arrogant approach that the higher order details of chemistry, the emergent properties are not something you have to worry about. But of course, that's not true at all. And so when you're thinking about chemistry, I think there's one thing in particular that is really important to emphasize, and that is elemental electronegativity. So this plot here is showing the electronegativity of, according to the Pauling scale, of various elements, or most of the periodic table. And at its heart, electronegativity is a pretty simple concept, really. It's just the propensity of a given element to attract electrons. And so, for example, for H2O, oxygen is more electronegative than hydrogen. So it grabs the electrons towards it, and you end up with an uneven distribution as a result. And this is the central thing that leads to the concept of redox chemistry. So you have oxidizing versus reducing species, and this emerges from their electronegativity. I should add that electronegativity is not a completely fixed concept, because it also depends on the oxidation state of whatever you're dealing with. But for our purposes, we can take it in these general terms. And so perhaps from high school, you remember oxidation is loss of electrons, reduction is gain. A classic example of a redox reaction is the oxidation of iron. So you have metallic iron reacting with atmospheric oxygen to form hematite. So reducing iron, having electrons grabbed from it and being converted to oxidized iron, as you see in this classic banded iron formation on Earth image. And so in a planetary context, I think it's good to be able to visualize intuitively what we think of as reducing and oxidizing environments as well. And so for me, the classic oxidizing surface is that of Mars. The clue is that it's rusted, the iron itself is rusted red by oxidation. And the classic reducing surface is Titan, which is, well, it's in false color here, but Titan has enough abundant hydrogen in its atmosphere that its conditions are extremely reducing compared to Earth or Mars or Venus. So there's a really basic fact of planetary evolution that follows from elemental abundances and this concept of redox. And I've tried to summarize it here in this cartoon. This is electronegativity on this axis and atomic mass on this axis. The areas of the circles correspond to the log abundance of whatever element you're dealing with. So things that will tend to reduce on this side, things that will tend to oxidize on this side. And I should emphasize this is a cartoon. There's not a direct correlation between a compound's density and it's the mass of the elements that compose it. But overall, this is something that's helpful to keep in mind. And the essence of what happens is that because iron is heavy, it sinks to the core. It tends to reduce. Hydrogen also tends to reduce, and it escapes to space. Things like magnesium and silicon bond with oxygen very early and then subsequently mainly remain in the mantle. And then you have these three elements here, of which oxygen is the most abundant and the most important, which we always should expect to a greater or lesser extent to build up in the surface and atmosphere regions of rocky bodies. And so I like to belabor this point because I think that sometimes we think of abiotic oxidation as this weird exotic process, but it's really not. It's just the basic combination of the abundance of elements we have and the fact that planets tend to differentiate. And it's also interesting to think that this depends completely on the details of stellar nucleosynthesis. If, say, lithium was more abundant than oxygen, the chemistry would proceed in the opposite direction with profound implications for the way complex chemistry and life has emerged on Earth. So let's look at a specific example of this now in the solar system. And I've picked a body in the outer solar system, Ganymede, which doesn't always get as much attention, perhaps as it deserves. So Ganymede is an icy moon. We believe it's differentiated to have an iron core, a rocky mantle, just like in the cartoon in the previous slide, and then a region where there's H2O and ammonia ice and some other volatiles, and an icy crust. And then on top of all of this, there's an extremely thin oxygen atmosphere. And this oxygen atmosphere emerges because you've got H2 on the surface. You have stellar photons, which are solar photons, which are bombarding it. And some of that hydrogen escapes to space. I should say, well, solar photons and precipitating particles from the rich plasma environment that it's in orbit around Jupiter. So yeah, just to make that point a little clearer, this is a plot of a photochemical calculation from going back to the 70s that imagined what Ganymede's atmosphere would look like if it was primarily photons that's driving this oxidation. And then these are observations from the 1990s that observed the air glow of atomic oxygen. From this, you can get constraints on the abundances of O2. And it's believed, based on these observations and most recent theory, that there's precipitation of plasma at the poles, which is primarily driving this for Ganymede. But it's still this basic process of hydrogen being lighter and escaping and oxidation resulting from it. So I think that's a nice example. I also think when talking about examples like this, it's good to remember that Ganymede has a near twin in terms of its mass, which orbits a different gas giant, which has a very, very different atmosphere. And so hopefully if there's time at the end, we can talk about why Ganymede and Titan have such radically different atmospheres. It's an interesting story. What am I doing for time? Okay. So, yeah, so that's some really basic chemistry concepts. Let's talk more now about, yeah, actually just backing up a couple of slides. I should say that there's two parts to this problem, right? You've got everything that's going on in the interior, and then there's the loss to space. I'm not going to talk about the interior part much, mainly because I think it's going to be covered better in other presentations here, but we are going to focus on saying a few words on the physics of the escape part. So the way to start thinking about atmospheric escape, or the way I like starting thinking about it, is to consider a planet and just an individual gas molecule that's somehow bound to that planet. Well, we know Newton's laws, so we can say if we want it to escape, we need to get it to the escape velocity, 2 times the gravitational constant times the mass of the planet divided by its radius. It's all square rooted. But then when we're dealing with a gas, we're not usually interested in individual velocities. We're interested in the bulk properties. So we compare this velocity with the thermal velocity, which is the Boltzmann constant times temperature divided by the molecule mass. And so if we take the square of these quantities and then back up a second, just have the ratio of these, we get a dimensionless parameter chi, which is fundamental for understanding what kind of escape regime you're going to be in. So you can do some algebra to show that this is equivalent to the ratio of the radius of the planet divided by the scale height of the atmosphere. Scale height of the atmosphere being its characteristic puffiness, large scale height extending to much larger radii. And so if you have a radius which is much larger than the scale height, you expect the escape would be harder. If the scale height becomes incomparable to the radius, then the atmosphere is barely bound anymore, and so a lot of different processes could remove it. And so there's a first type of atmospheric escape called Jeans escape, which I'm going to talk about qualitatively, but I'm not going to give you the maths on it, mainly because I think Jeans escape is not that important under most circumstances. It's nice because it's theoretically elegant, but it's generally useless for understanding escape in a lot of contexts. There are some cases where you need to consider it, but not most. So the essence physically of what's going on with Jeans escape is that you have a Maxwell-Boltzmann distribution of velocities, and then you have some tail of this where the very fastest molecules are getting to the point where they exceed the escape velocity. And so Jeans escape says that I have gas being lost from my atmosphere at the very top where this tail of the distribution is being depleted, but things are resetting back to thermal equilibrium quick enough that the tail never actually gets depleted. It always just looks as though it is. If that was no longer the case, then you would start to have a non-thermal distribution of molecules, and you would need to do more complex theory. But that's kind of the essence of Jeans escape, and it's, as I said, very slow under most circumstances. So if Jeans escape is often not the main thing to care about, what are escape processes that really matter for sculpting planetary atmospheres? I've listed three that I think are perhaps the most important here. The first is impact-driven escape. So basically, you're forming your planet through accretion. You have impactors coming in, and depending on their velocity and their mass and the mass of the atmosphere they're impacting, they can remove more or less of it. And if you imagine a high-velocity impactor, which is not getting to the size of a moon-forming impact, but still substantial kinetic energy delivered, then the maximum atmosphere that it can remove is going to be the tangent plane for where it strikes, because you can't easily transport energy over the horizon. So you can develop a theory for escape where you take this fact into account. And it's kind of complicated for impactors because they frequently can deliver as much or more than they're taking away. And so whether or not you're actually gaining an atmosphere or losing it due to the inflow of impactors depends on the details of their velocity and the mass of the atmosphere that you have. But I think an important thing to emphasize it for, this is the things I'm really going to be focusing on in this presentation, this chemical evolution of atmospheres. Under most circumstances, well, impactors cannot directly fractionate the gas itself. They can, if you have some volatiles like H2O is liquid water on the surface, and then other things as gas phase, then in that sense they can fractionate, but they won't separate gases from each other. The second case is XUV-driven hydrodynamic escape, and the essence of this type of escape is that you have the highest energy stellar photons, so a very small fraction of the overall flux you're getting from the sun, but a very important one, strikes the upper atmosphere and gets absorbed, heats it up to very, very high temperatures, and then the scale height of that upper atmosphere, its puffiness gets so large that then it can escape hydrodynamically as a gas. And we think this is a very important mechanism for sculpting planetary atmospheres early on. I say we think because although we have some observations of this going on for larger exoplanets, there's still none for the terrestrial cases. And one of the things that really excites me about the next decade or so of exoplanet observations is that we may, for the first time, start to get observational constraints on the theory that's being developed for this process. And then finally, there's non-thermal processes, which is in a whole lecture series in itself. Really, they're varied and quite complex. They're mostly important for elements heavier than helium. So, for example, the MAVEN mission, which is in orbit around Mars right now, is studying escape of CO2 and water from the Martian atmosphere. And in that situation, closer to present-day conditions, non-thermal escape processes are dominant. But when you're interested in things going early on in the really bulk modification, XUV-driven hydrodynamic escape is particularly important. So this is the one process that we're going to focus on more here from now. So for this process, if you know the XUV flux from the host star, and this is just a case of knowing the spectrum and then truncating at a certain wavelength and summing up all the photons in that region, you have some efficiency factor or fudge factor, if you want to be less charitable, that you include here, which incorporates complex physics like three-dimensional effects. And then you have the potential energy of a molecule of the gas you're interested in, which is frequently hydrogen. By expressing it in this way, you have this energy-limited formula, which tells you the mass flux in kilograms per meter squared per second, which is going to escape. So that's all very well and good, but it can get more complex because when you have atmospheres that are not single constituent, which is the rule rather than the exception for low-mass planets, you also need to take into account drag of heavier species. So for example, if you have hydrogen and oxygen together, and hydrogen escapes extremely vigorously, it will drag some of that oxygen away with it as well. Generally speaking, the amount that gets dragged is less, but in some cases it can be very important. And so this schematic on the right-hand side shows what's going on in these kind of scenarios. You have transport from the deep atmosphere, your key species, in this case, H and O. Eventually you reach a point in the atmosphere called the homopause, which is the point at which gases no longer mix readily together. So once you get above the homopause, things evolve so slowly that a gas like hydrogen can puff out according to its own scale height, and heavier gases like CO2 will decrease down to separate away from it. We don't see this in the lower atmosphere because turbulence is just so fast that it completely overwhelms it, but it happens when you get high enough. And once you reach this homopause, as I said, if you have high enough fluxes, you can drag various species along with the one that's escaping. I won't go into the equations that govern this in too much detail, but there's actually two main ways of expressing this. One uses a crossover mass, and the other uses a crossover flux. I find this way infinitely simpler than trying to get your head around crossover mass, and so this is what I tend to stick with. But basically, this is showing the escape fluxes for a light species and a heavy one. This is the mass flux, this little phi. The m's are masses of the individual molecules. The average, the m over bar is the average value. X1 and X2 correspond to the molar fractions of the two species. And then these parameters, this one and this one, are defined here and here. So the H is the scale height, which we already mentioned. And then this B is critically important. This is the binary diffusion parameters. So physicists in the lab from the 50s and perhaps further back have been measuring how gases diffuse with each other. And so we have experimental data which allows us to constrain this for whatever elements we're interested in. So this drag process is important for oxygen and hydrogen. It's also really important for thinking about traces of escapes that may have occurred in the past. And you've heard a little bit about this already in this morning session, but deuterium, which is used in nuclear reactors and also for party tricks involving ice cubes that sink to the bottom of glasses of water, is a isotope of hydrogen, which is stable and will get dragged readily along with hydrogen when it escapes. And so if you look at a plot, I think Kevin had this in one of his slides, but this is D to H on this axis and then nitrogen ratios on this axis. Don't worry about the nitrogen too much. But the deuterium to hydrogen, so we have solar and Jupiter right down here. Earth and Mars is over here with elevated deuterium. Mars' atmosphere is up here. And then Venus is all the way over this way. It's massively enriched in deuterium compared to the solar standard. And this has to be a sign that to a greater or lesser extent, Venus has had substantial water loss. And I think another thing that's very exciting for exoplanet observations is that with James Webb and possibly with ground-based facilities, we think that for the most enriched cases, the more Venus-like exoplanets, we're going to be able to observe this directly. So hydrogen, well, HDO and H2O have distinct absorption spectra because the vibrational and rotational modes are different because the masses are different. So there are certain regions of the spectrum where you can look and see differences between a very deuterated atmosphere and a more solar-like one. So this is something that's going to be very exciting once we have the next generation observing facilities coming online. So let's talk a little bit more about Venus. Venus perhaps could have been habitable early on. The reason for this is that the sun evolves on the main sequence. It gets brighter with time. And so there have been models which have estimated, perhaps as recently as 0.7 gigayears ago, it could still have had surface liquid water. But eventually you get to a point where the sun gets so bright that the planet can't sustain itself against a runaway greenhouse where all the oceans boil off and go into the atmosphere. You get H2O in the high atmosphere, and then hydrogen and some oxygen escapes. The sun oxygen part is important because most of that oxygen, even early on when the XUV flux is really strong, most of that oxygen won't escape. Most of it will, or a large proportion of it should stay on the planet. And this is a problem for this model because we don't observe oxygen, significant amounts of oxygen in Venus's atmosphere today. So another possibility for Venus's evolution is that all this stuff happened very early on when there's a magma ocean phase. If you have a magma ocean, so if you have molten surface, then it's much easier to mix gases in the atmosphere downwards. And then you could have just sucked all the oxygen up into the mantle and you would get around this problem. And it also seems to fit noble gas isotopic ratios a little better as well. And I would argue the nitrogen inventory on Venus is more consistent with this scenario because for Earth, we expect that it would have exited a hot magma ocean stage quickly, and you could have substantial amounts of nitrogen trapped in the mantle as a result. Whereas for Venus, if you're oxidizing over time, we think this would flush nitrogen out into the atmosphere and leave us with the roughly 3 times inventory of nitrogen in Venus's atmosphere today versus what we see for Earth. Although Venus needs much more data, and more missions in future will really allow us to constrain a lot of these processes. Okay, so this is my one Earth slide. Earth, you may have noticed today, has not lost all its oceans to space. A primary reason for this is that we have an atmosphere, 1 bar atmosphere, particularly the 0.8 bars of nitrogen, which means that water forms clouds, condenses, and gets cold trapped out before it reaches the upper atmosphere. The stratosphere is extremely dry. And so because the upper atmosphere is dry, you don't have leakage of hydrogen and oxygen to space that would lead to extensive water loss. And it's a fascinating question to ask of whether this is always the case, because although it looks like deuterium to hydrogen is pretty close to carbonaceous chondrite meteorites for Earth, there is actually significant leeway in there to still have water loss. And again, this is something Kevin was touching on. So there could have been hydrogen loss. There may have been a role of hydrogen and methane, perhaps to significant levels early on. And then there's this other fascinating point, which I still really don't know what to make of, but there is papers that have been published claiming that Earth's air pressure 2.7 billion years ago was constrained to less than half of modern levels. And so I won't go into the details of how they made this measurement. It was using volcanic amygdales. But all I will say is that if this observation is true, then it has significant implications for water loss, because if you have a very thin nitrogen atmosphere, then you will start to propagate water to the high atmosphere. You lose your cold trap, and then you should have lots of hydrogen escaping. Let's talk about Mars a little bit. So Mars also generally has H2O cold traps, which is kind of interesting because it has a much, much thinner atmosphere than Earth does, but it's also a colder planet, and so this part more than compensates for this part. Mars is oxidized, as I've said, although exactly how oxidized is still a subject to debate. As you can see by looking at this drill core from the MSL rover, you have oxidized iron on the surface, and then centimeters or millimeters deeper below that, you see reduced iron, more of the type that we see on the lunar surface. But on Mars today, there are photochemical feedbacks, which mean that oxidation is prevented if you try to break apart the H2O in the lower atmosphere. And so this was thought to be a problem for a long time, but there's been recent work which has given new insight into this, because models and study of observational data has shown that H2O should be intensely lost into the high atmosphere during dust events. And when it gets to the high atmosphere, the constraints on escape that come from these feedbacks no longer apply. So I think it's a good model for Mars's early history, that it may have lost a lot of water through intermittent events rather than its long-term steady state. This plot is just showing through Martian time the hydrogen escape flux and the ultraviolet flux, showing the correlation. And then this plot is showing the dust flux into the atmosphere. So the argument is the dust is the cause of the increase in H loss to space. And I'm not going to have time to cover this in detail, but because of the fact that Mars' interior seems to be really quite reducing, the early Martian atmosphere could also have been episodically very reducing, with significant possible climate implications. And this is important because we know there's all this evidence for flowing liquid water on early Mars. I've summarized a bunch of geologic features here, but there's on top of this, there's argued to be evidence for oceans, which is provocative and interesting, but it does run into some trouble with the constraints from D2H, which limit the total amount of water which should have been present on the early Martian surface. So this is very much an active, ongoing area of research. Okay, so I've got a couple of little bitty slides, and then the final part will be talking about exoplanets. We are finally going to get onto exoplanets here, but this is just something I wanted to highlight from a recent paper by It's actually an undergrad who was working at the time, is now a PhD student at MIT. And the aim of this was to look at if you have water loss from, if we think we understand water loss from higher mass objects, and we know we understand water loss more or less from comets because we can observe it directly, what happens in between as you transition down through Ganymede mass to this regime? It's interesting to theorize on because among the important things that should happen are that if you have a lower mass for your object, then when all the water is getting into the atmosphere in a runaway greenhouse regime, the atmosphere should puff out. One of the things this can do is to create a larger radiating surface, so inhibit a runaway greenhouse from happening until much longer. And so one of the outcomes of this study was that there should be a much larger range for potentially habitable conditions for exomoons than there was thought based on previous work. Although it's always transient because they're losing the water as they're undergoing this process. Another related but somewhat ad hoc topic that I just want to mention quickly is sulfur. I had sulfur on one of those slides way back, but I've avoided talking about it since because it's really complicated. And from a Redox perspective, it's harder to constrain. But it also has significant potential for how we think about things like diagnosing surface liquid water. And so in this study, the idea has been to say, if we have a planet with a permanent sulfate haze layer, can that tell us something about the presence or absence of liquid water on the surface? And we think that it can be shown quite strongly that if you observe sulfate hazes in an exoplanet remotely, then that places strong constraints on the total amount of water that's present on the surface. Okay, so I think I'm running out of time a little bit. I do want to very quickly talk about water loss from exoplanets as well. The essence of this topic was talked about in a nice amount of detail by Vicky. The basic challenge is that around certain star types, M stars in particular, we think that this long pre-main sequence phase where there should be significant amounts of loss to space, and this could lead to the development of abiotic oxygen atmospheres. So this was something that we looked at quite recently, modeling not just the atmosphere of the planet, but also its interior. And the essential upshot of the study was that you definitely can get abiotic oxygen in some circumstances, but if you're sufficiently iron-rich in the mantle, or if your planet is water-rich, then all of that's going to get sucked down into the mantle and remain there. And in addition, if your planet's slightly further away from its host star, it's much, much less likely that the abiotic oxygen is going to build up. And so based on this, you can build a kind of executive summary for the known exoplanets. This list needs to be extended now, thanks to Tess. But this is what we would estimate for the potential of buildup of O2 for all these cases. Obviously, we're all interested in the habitable zone, potentially Earth-like planets, because there might be life there. But as a planetary scientist, the most exciting ones for me in the short term are actually ones like this planet, which will not be habitable, but it's very observable. So it's going to be a direct way to constrain our predictions before we get to the point where we can really diagnose the Earth-like cases. And so I'm not going to get into details of how we're going to observe this exactly, but there's a number of possible techniques. Do I have time for one final point before finishing up? This is just one of these like, oh, we have a habitable zone. What about another habitable zone? But I think this is potentially a really important one because we're really used to thinking about temperature and surface liquid water. And I think that we should seriously be talking about redox state of the surface and atmosphere as another really key constraint. And so we know that certain planets can hyperoxidize and get to the point where if you do get any complex chemistry, it's just going to be broken apart by extreme oxidants very quickly. And likewise, if you're underoxidized, you're either going to have so much hydrogen that there's no solid boundaries, or you're going to have a situation where you build up some interesting precursors, but there's not much free energy sources for life to get started on it. And so I think there is something special about Earth that involves a combination either through time or different spatial locations of both oxidized and reduced reservoirs. So, okay, just to finish up then, in conclusion, gas giant atmospheres are not in chemical equilibrium, but they're diluted, so they're not great places to search for life. Rocky planet atmospheres are almost always out of chemical equilibrium to a greater or lesser extent. In galactic terms, they're always relatively oxidized. Venus and Mars, we think both underwent extensive water loss and surface oxidation. For Earth, questions still remain. But then for exoplanets, in some cases, we predict extreme oxidations, which has major implications for false biosignatures and also the likelihood for these cases that we're going to get prebiotic chemistry in the first place. Thank you.
We got time for some questions?
For someone that doesn't study atmospheres a whole lot, how can I visualize what you mean when you say that one headline that the atmospheric pressure was like half of what it was today, or 60% of what it was today?
So the question was, how can you visualize that the atmosphere was half of what it was today?
Right,
yeah. Yeah. Do you mean from the perspective of understanding the measurement or understanding what that would be like?
What that would be like? It sounds like it's usually discussed in terms of pressure, lower pressure, higher pressure, what that means for the overall picture. Yeah.
So I should first of all emphasize that that's one study. I think it's quite controversial in some ways, and so we're far from understanding the history of Earth's pressure through time. But if we were to say that the pressure was 50% less, I mean, physically speaking, we're talking about for a given gravity, the total column amount of molecules that you have present there. So you can convert pressure to total mass of the atmosphere for a given gravity. But then what's really interesting about nitrogen is that just ties into so many other ways in which the planet behaves. So, okay, you have a lower atmospheric pressure. You might initially not care about that, but it's also going to change your dynamics because you might think that the temperature difference between your poles and your equator will increase because there's less mass of the atmosphere to do that transport. As I said, the way that the convection behaves is going to change because your plumes from clouds will travel higher up into the atmosphere. And then even the radius balance can change because nitrogen is good at broadening the spectral lines of things like CO2 and H2O. And so just one little change for gas that often is regarded as a little uninteresting can lead to a lot of profound differences in the way that the rest of the climate evolves.
So actually related to the N2O trap, we mentioned if you decrease the amount of N2, then you let more water into the stratosphere, right?
Mm-hmm.
So how does that change if the overall temperature of the surface is cooler?
Yeah, so then you have to think about the thermodynamics, and there's actually a neat dimensional analysis you can do that it basically comes down to the ratio of the latent heat of the condensable substance to the sensible heat of the non-condensing substance of the surface. If that ratio gets large enough, then you get to the point where you get stuff in the high atmosphere. If not, it doesn't. But temperature is definitely extremely important as well. It's both pressure and temperature that you have to care about.
So my question is a bit broad, but do we have any constraints on how oxidized or reduced the planet can actually be? Are there any observations by atmosphere or something like that? Like, what are the extremes?
Yeah, that's a great question. So I find it hard to imagine ways you could get more reduced than a gas giant planet. Maybe someone will be able to come up with one, but I can't off the top of my head think of how you would do it. So I think hydrogen dominated for me is the reducing limit on one side. Then how oxidized you could get? Well, if you lose all of your hydrogen and you just have oxygen remaining, I don't know how you could fractionate oxygen from fluorine. So I think oxygen dominated is in my head is as far as I'm able to go for thinking about that limit. It's probably completely desiccated with just traces of things like hydrogen peroxide left. I should probably add on top of that as well that I'm talking about bulk composition, but when you get into the details, many more things are important, like kinetics, the reactability of species, whether you have like the geochemistry in certain contexts leading to more rapid oxidation or not. Like I'm doing intentionally a very broad brush kind of astrophysics type approach to this, but as we're going to be hearing in the later talks, a lot of once you get to looking at the geologic record on Earth, all of those details become really important.
Do one last question? Or there was one at the back?
Yeah. So for the
So transient activity for XUV fluxes or for the other stuff, like coronal mass ejunctions and things? Yeah. Yeah, that's a good question. So we focused on XUV and we bounded it by looking at a extremal case and a minimum case. That, I mean, honestly, we need better XUV observations of a host of M stars, have a better model of how it evolves in general, but we did the best we could with the data that was out there. We did not take into account coronal mass ejections. There are a number of groups that are attempting to pursue this now. It's an interesting area. It can get more complex because you really have to think about the non-thermal processes that I kind of glossed over in that middle slide. But I do think just from an energy perspective, if you do the back of the envelope calculation, if you're thinking about hydrogen removal in particular, XUV-driven escape should be more important than coronal mass ejections. I think where they become really important is once you've removed hydrogen and you have heavier atmosphere, maybe nitrogen or CO2 dominated, and then these non-thermal mechanisms are some of the only things that for a planet of a significant mass that you can have to remove things like carbon and nitrogen effectively.
Well, let's thank Robert again. Cool.
Thanks.